Welcome back to ECE 320A. In this video, what I want to do is summarize what we've seen in recent material, and that is to summarize the Laplace transform of exponential and sinusoids and start to become more comfortable with what these time domain waveforms look like in the frequency domain. Again, what we want to do is start becoming comfortable moving back and forth between the two domains. We have the time domain and we have the frequency domain. And if you want to, maybe what you want to do is when you're in the time domain, sit in one location of the room or part of the house or apartment. And when you go into the frequency domain, move locations physically so that you feel like you're doing something different. Play in the frequency domain when we're in the frequency domain, and then you may have to go back into the time domain. But we want to get comfortable going back and forth in those two domains. And to do that, we can, if you get comfortable with the Laplace transform of the exponential, where this exponential could be real or imaginary, then we will start to become very comfortable with what's happening relative to the Laplace transform operation, moving from time domain into frequency domain. Here I'm simply representing a table. Now I'm reordering these rows a little bit, but we've already derived the Laplace transform of this generic exponential. That was our fundamental building block in an earlier video. That now, if we plug that into the definition of the Laplace transform and evaluate, we end up with this Laplace transform of an exponential being 1 over s minus gamma. If we replace gamma now with different values of sigma, suppose we let gamma be a negative number, then we have a decaying exponential in the time domain, and in the frequency domain that gives us this transformed expression or transform expression 1 over s plus sigma. And not only do we want to think about the time domain, the second column, e to the minus sigma t, that's a decaying exponential in the time domain. The third column gives us the transform connected to that time domain waveform. So now we're running back and forth between our time domain location and our frequency domain location. But we can also think about the frequency domain location in terms of poles and zeros, or values of s that cause the denominator to vanish. Those will be our poles, and those we will indicate with x's in the complex s plane. We can also think about values of s. We'll deal with finite values of s that cause that expression to vanish, which then that says what values of s cause the numerator in this transform expression to vanish. Here, there's no s even in the numerator, so there are no finite zeros, and we'll represent finite zeros with open circles in the complex s plane. If we're now putting poles and zeros in the complex s plane for this first row in this transform table, we will see that we only have one. The denominator is a polynomial of power 1 in s, or a first order polynomial in s. We have s to the first power. We have s plus sigma equaling 0. We solve that for s, and we get s is equal to minus sigma. That's the location. If we stepped on that particular location in the complex s plane, we would go unbounded. That's the value of s that causes that transform expression to go unbounded, and it corresponds to the value of s that causes the denominator to vanish. So whenever we step on these x's, that means we're going way up. We're going through the roof. If we look at the opposite, the first row was a decaying exponential. The second row is a expanding or a growing exponential, e to the sigma t. Sigma is positive. That transforms into the frequency domain as an expression 1 over s minus sigma. the pole of that is now the value of s that causes the denominator to vanish, or we set the denominator equal to 0 and solve for all the s's that make that true. In this case, there's only one such s because the denominator polynomial is of a first order. It just has s to the first power. So we have s is equal to sigma. Now if we went over into the right half plane of our s-plane, now I'm going to be talking about right half plane, that's to the right of the imaginary axis, and left half plane, which is to the left of the imaginary axis. Now if we looked at a pole appearing in the right half plane in the frequency domain in the s-plane, that corresponds to an unbounded exponential in the time domain. Contrast that with the first row in this table where we have a pole in the left half plane. That now corresponds to a decaying exponential, or somewhat better behaved waveform as a function of time. The second row in the time domain corresponds to an unbounded waveform in time. If we now let gamma be imaginary, or let gamma equal j omega, where omega is now a positive number, we're now looking at e to the j omega t, and you could think of this as a rotating phasor. If you found the magnitude of that complex number, e to the j omega t, by using Euler, you would find that the real part squared plus the imaginary part squared, square rooted, would have a magnitude of 1, and you're simply changing its location on this circle of radius 1 in the complex plane if you were to think of this as a function of time. If we now look at that e to the j omega t in the frequency domain, or after finding its Laplace transform, we find that we have 1 over s minus j omega. The pole now of that expression is the value of s that causes the denominator to vanish, which if we set s minus j omega equal to 0, that becomes s equal j omega, and that's the reason for our x on that positive side of the imaginary axis. Contrasting that with the fourth and final row in this table, we now have e to the minus j omega t. Again, the magnitude of that complex number is 1. It's now just spinning opposite to e to the j omega t. In the transform domain, or if we Laplace transform that, we end up with 1 over s plus j omega. The value of s that causes that expression to go unbounded is the value of s that causes the denominator to vanish, and that's when s is equal to minus j omega, or we now have this x, or pole, at the negative imaginary axis, or on the negative imaginary axis at minus j omega. We can use these last two rows to actually build up our understanding of a cosine's Laplace transform and a sine's Laplace transform, relying on Euler's way of representing cosine in the form of a sum of complex exponentials. And we've done this in a previous video, so I will simply give the result. The Laplace transform of the cosine omega t is s over s squared plus omega squared. Now we have an s in the numerator. We have s squared in the denominator, so we should have a second order, or two values of s that cause the denominator to vanish. We actually have one value of s that causes the numerator to vanish, and we call those different things. The values of s that cause this expression, this transform expression, to go unbounded are the values of s that cause the denominator to vanish. Those are the poles. That's when s squared plus omega squared is equal to 0, or when s squared is equal to minus omega squared. If we take the square root of both sides, we have s is equal to the square root of minus omega squared. We can factor that product into a product of radicals. We now have the square root of minus 1 times the square root of omega squared. The square root of omega squared is plus and minus omega, and the square root of minus 1 in electrical engineering, we say that's j. So the two values of s that cause that transform which is the Laplace transform of a cosine, to vanish our plus and minus j omega, the 0 is the value of s that causes the numerator to vanish, which in this case, the numerator of our expression is this is a finite 0. The finite 0, the finite values of s that cause that expression to vanish will be the values of s that cause the numerator to vanish. In this case, the numerator is s. It's a first order polynomial in s, and we can set that polynomial, which is just s, equal to 0, and now we've trivially solved for the value of s that causes that numerator to vanish, which is a 0. If we put those poles and zeros in the complex s-plane corresponding to the cosine's Laplace transform, we end up with poles that are mere reflections of each other. We have one at j omega and its cousin or twin at minus j omega, and we have a 0 at the origin. Here is our 0, and we have two poles because our denominator was a second order in S. And that's now what the S-plane pole 0 diagram looks like for the Laplace transform of a pure cosine. We have two poles on the imaginary axis located symmetrical with respect to the origin at plus and minus j omega, and we have a 0 right at the origin. We can do the same trying to find the poles and zeros of the sine waveform. Again, we've already derived that Laplace transform. Let's now just state it. We now have omega over s squared plus omega squared, and I hope it's clear that the poles are exactly where they were for a cosine waveform at the same frequency. So anytime we have a frequency of omega in a sine or a cosine, we're going to have, and this sine and cosine is a pure sine and cosine, there's no damping on that sine and cosine, then we will end up with poles and zeros on the imaginary axis at plus and minus j omega. I'm sorry, we have poles at plus and minus j omega. The zeros, what are the finite values of s that cause the numerator to vanish? Well, there's no s in the numerator. There are no finite zeros. There are no finite values of s that cause omega over s squared plus omega squared to vanish, which is what makes the numerator vanish when we replace or put s at some location. There is none, but now we can sketch the pole 0 diagram for the Laplace transform of the sine waveform, and now we have j omega and minus j omega. There are no open circles. There are no zeros in that transformed operation, and now we have poles in the complex s-plane at the exact same location as we did for the cosine as we do for the sine. The difference is there are no finite zeros for a pure sine wave's Laplace transform. There is one finite 0, and it's at the origin when we look at the Laplace transform of a cosine waveform. And that's what we need to start getting comfortable with. The pole 0 diagram associated with sine, pole 0 diagram associated with cosine, and these pole 0 diagrams for real poles, one corresponding to a decaying exponential. That pole is in the left half plane on the real axis, one corresponding to an unbounded exponential, which results in a pole in the right half plane on the real axis. And we'll continue, hopefully, to become comfortable with those concepts as we move throughout the course.